Okay, for the circuit shown below, calculate the currents I. Okay, what we can see here, this is only one loop. Okay, one loop with two batteries. This is two battery. So we have one loop with two batteries together. So we can, this is considered a complex circuit. Yeah. So this is a complex circuit. It's for complex circuit, we need to use Kirchhoff rule, Kirchhoff law or Kirchhoff rule to solve the questions. Okay, so because like we have two batteries, how are we going to use a normal method? Yeah, so certainly this is a complex circuit. We need to use Kirchhoff law or Kirchhoff rules. Yeah, Kirchhoff rules. Well, first of all, what's the step to solve? The problem solving strategy is we need to label first. Label, then we apply the first law and second law. Then only we solve the questions. So first of all, you need to label. Label the diagram. What do you need to label? What do you need to label? But before that, we look at this is considered as how many loop? Only one loop. Because we have questions with one loop or two loops. Like this one, we have two loops. You see that? We have two loops. But this question is only one loop. So for one loop, you must know that if one loop, there's only one current. Unlike the two loops have three current, I1, I2, I3. One loop has only one current. So that means there's only I. There's no I1, I2, I3. There's only I, one current only. Okay. And then we there's no junction. Yeah, like for one loop, there's no junction. There is no, because only one current, one circuit. There's no several current meet up to combine, become a bigger current. No, there's only one current in one circuit. So that there's no junction, there's only one current. So for first law, which is the junction law, since it has no junction, so for one loop question, there's no equation. There is no equation for first law. No equation for first law. So, but for the second law, which is the loop law, yeah, total E equal to total IR. Okay, for the second law, there's only one equation. One equation because there's only one loop. You understand? There is only one loop, so there's only one equation. So remember this. Okay, so I want to write that over here. This is considered to be a one loop questions. One loop has only one current, so it is I. And then first law, there's no equations, but for second law, there's only, and they consider to be only one loop, so it only has one equation. Okay, it only has one equations. All right. So this is a thing I want to do. Okay. So first of all, you need to label first. Yeah. Remember, you need to label. Label what? Label all the EMF, label the current, label the loop direction. Yeah. Label the EMF, label the current, label the loop direction. That's the first thing you should do. And then you apply the first law, then apply the second law, then only you solve the equations. Okay. Right now, but this question only one loop, that means there's no first law because no junction. Yeah. So after we label, we straight away go to build equation for second law. Okay, so now let's first of all we label. Okay, we need to label the EMF direction. So how to label the EMF direction? Okay, EMF direction. EMF direction is always that means from negative to positive. Okay. Maybe we can label this as this one as, this is considered to be E1. Okay, E1. and this one is E2, yeah, E2. Okay, and then this is the internal resistance. You understand? This is the internal resistance for the battery. 2 ohm is the internal resistance for battery E1. So maybe you can draw like over here, yeah, over here. So these 2 ohm and 4 ohm actually they are internal resistance for the battery. So maybe you can label this as you know, this one as R1, this one as R2. Okay, and then this 3 ohm and 7 ohm actually they are external resistance, so we can label this as R1. Yeah, this one's as R2. All right. Okay, so now label the EMF direction. EMF direction is always from negative to positive. EMF is always negative to positive. And then for E2, also from negative to positive. That's the EMF direction. Okay, this is the direction for E1. This is the direction for E2. Okay, always from negative to positive. Now we label the EMF already. Now label the current. Label the current. So current always flow from, current always flow from high potential. Always flow from high to low potential. Current always flow from high potential to low potential. So look at this battery. Which battery is stronger? Which is a bigger battery? Is it E1 bigger battery or E2? Of course it's E1 because it's 12 volt, isn't it? 12 volt battery is higher voltage, higher potential difference compared to E2 is just 4 volt. So the current should actually, current always flow from positive to negative terminal, right? But you're looking at this is only one loop. If only one loop, that means it's only one current. If only one loop, there's only one current. You cannot have you cannot say that, oh, you have two battery, then there'll be two current coming out from the battery. Yeah. Oh, E1 release current I1, and then E2 release current I2, and then these two current come and collide with each other and then explode at this resistance. I1 and I2 collide with each other and then become collision, and then here burn off. No, there's no such thing. One circuit cannot have two current. One circuit or one loop has only one current. Has only one current. Okay, so one circuit has only one current. So don't say that, oh, you have two battery, that means you must have two current. No. No. Instead, this is what happened. This is what happened. Let me write down. So instead, this is what happened. This battery 12 volt is bigger battery than this E2. E2 is a smaller battery. E1 is a bigger battery. So normally current flow from high potential to low potential. That means this E1 considered to be higher potential. Yeah, it actually pushes the current to go in the direction of E1. The current, we can say E1 has a bigger motor, E2 is a smaller motor, but they are driving the current in the same circuit. So since E1 is a bigger motor, of course the current will follow the bigger motor instead of the smaller motor. So the electric current will be pushed around even harder by E1 compared to E2. E2 is pushed with smaller, considered pushed with a smaller energy, smaller force. So E1 has a bigger force. It will push the current in the direction following the direction of the E1. Okay. So I can say that the current normally follow the bigger EMF. Yeah, the current direction always follow the direction of the bigger EMF rather than the direction of the smaller EMF. So the current actually should flow in the direction of E1 instead of E2. Okay, so this is the direction of the current. It's being pushed even harder by E1. Okay, and then going through. Okay, label the current near the resistor. Why we need to label the current near the resistor? Because later on we are going to use the Kirchhoff's second law, the loop law, that we need the direction of current with resistor. Then only we can know the direction of the resistor. So you must label the current at every resistor. Okay, for every battery you need to label the direction of the EMF. For resistor, you need to label the direction of the current. Because we need the direction of the current later on for the second law. Okay, the internal resistance also you need to label the direction of the current, because the internal resistance is much like the internal resistance of battery is much like the external resistance battery. The internal resistance of the battery is much like the external resistance. It needs the direction of the current. Okay, so you must label the direction of the current near the internal resistance as well. Okay, so like R2, what's the direction of the current? As I said, this current will normally follow the bigger EMF, so it's being pushed harder by E1 compared to E2. So the current is being forced. The current is being forced in the opposite direction of E2. The current will flow in the opposite direction of E2 because this EMF2 is only a very small voltage. Yeah. So this current will flow to the right through the internal resistance R2, and then for 7 ohm external resistance R2, the current is also in this direction. Yeah, going in this direction. And then for R1, this internal resistance current is this way. So this current normally follow the bigger EMF, and you need to label the current near all the external resistance and also the internal resistance. Okay, whereas for battery you need to label the direction of the EMF, this one. Okay, I think you need to put different color, maybe this one color. Yeah. Okay, so I label already the EMF direction and also the current direction. Now I need to label the loop direction. All right, so the loop direction I need to choose. Normally the loop direction it follow the direction of the current and follow the direction of EMF. Okay, so why we need to follow the loop direction, need to follow the current or EMF, so that we can get as many positive value as possible. Normally, so if the loop direction follow the EMF or follow the current, then we will get more positive EMF or positive IR when we do the equation for second law. So try to make the loop direction follow the current and EMF. Try to follow the current and EMF so that we get more positive E and positive IR. Yeah, we try to prevent the loop direction opposite direction with the EMF. If that case, you become negative value, a lot of negative in your equations. But actually, it's not wrong. Even though your loop direction is opposite with your EMF, you want to put this loop direction anti-clockwise or clockwise. Yeah, you want to put the loop direction anti-clockwise, or you want to put the loop direction clockwise. Both never mind. Both accepted. It's just that if you put your loop direction like this one, loop direction opposite direction with the current direction and EMF direction, then you will get a lot of negative value. Then your equation is not so beautiful. So try to let your loop direction follow the direction of the EMF, and also follow direction of the current. So for this case, I try to make my loop follow the current and EMF. So I can see that the majority of the current is in the anti-clockwise, and also the EMF also, this one also considered to be anti-clockwise, isn't it? So I make my loop anti-clockwise as well. Then I will have many positive E and positive IR. Understand? There's only E2, only E2 is negative. Only E2 is negative. But majority is positive, isn't it? So your equation is more beautiful. Okay? That's the explanation for all. Okay, I have done label the EMF, done label the current, done label the loop. Now is my time to build equations. Okay, so as I said just now, one loop there's no junction, there's only one current. So we no need to use the formula current in, total current out, because there's only one current. So there's no I1, I2, I3. Understand? This I1, I2, I3 is we only use this if we have two loops. If we have one loop like this, there is no several current. There's only one current. So we can skip the first law. We go to the second law. The second law also only has one equation. Okay, because there's only one loop. Okay, only one loop. Okay, now we build equation for second law. Okay, so using the second law, okay, using this loop direction. Okay, the second law is loop law. Total E equal to total IR. Total E equal to total IR. Total IR. Remember this R. This R consists of both external resistance and internal resistance. It's not just the external resistance. You also consider the internal resistance of battery. Okay. Good. Now we are in here doing the equation for second law. Equation for second law. There's only one equation. Only one equation. Okay. So using this loop direction, which is anti-clockwise. Okay. Maybe I should put more arrow. Okay. This one is direction to the above here. The loop is direction to the left, and then here is direction downward. Here is direction to the right. And then over here is direction upward. Okay. Now let's look at total E. Yeah, total E. So how many EMF we have in these equations? How many EMF? Okay, maybe this one I should put it like that. Okay, how many EMF direction? How many EMF we have in this loop? There's only two battery, right? So we have two EMF. So for E1. So E1 is positive or negative? Positive or negative? Remember, as I told you before, if go back to my lecture video, I explained about this already. Yeah. Okay. So is it positive E? When is it positive E? When is it negative E? Positive E, positive EMF when the EMF is in the same direction with the loop. But when the EMF is opposite direction with the loop, it becomes negative E. Understand? Look at this one lah. So look at this E1. E1, yeah, is to the left, from negative to positive. That's why we need to label. We need to label the EMF. Then only we can compare the direction of the EMF with the loop. Understand? That's why we need to label everything first before we can build the equation. Don't skip the label step. Understand? Okay, the label is very important. So now, this EMF is to the E1 is to the left. The loop direction at the top here, the loop direction is also to the left. So it's same direction. So when same direction, when the loop direction and EMF same direction, they become positive EMF. So this EMF1 is positive. So we put it as positive. So very simple, is it? Positive E1. Okay. And then how about EMF2? Look at EMF2. EMF2 is to the left, from negative to positive. To the left. But the loop direction, look at the bottom one, not look at the top one. This loop direction means you are traveling along the loop. You understand? But anti-clockwise direction. Yeah, like this one, go to the left, down, right, up. it's like starting from this point, then you go this way to the left, and then down, and then to the right, and then upward, and then upward. That's what we call the loop direction. Yeah, you are traveling, let's say, from one point here. You go along this point, go to the right, go to the left, go down, go right, go up. So anti-clockwise direction. You understand? Okay. So let me wrap it off. Okay. So all right. So now look at E2. E2 direction is to the left, but the loop direction is you are going from to the right. Yeah, you are going to the right. Yeah, going to the right. The loop is to the right, but EMF2 is to the left. So EMF2 is negative. EMF2, this EMF2 is negative because the EMF and loop is opposite direction. This EMF2 is opposite direction to the loop. So when like opposite direction is negative EMF, negative EMF. Understand? So that one is a negative E2. That is the negative E2. Understand? Now we have done. No more battery, no E1, E2, we don't have E3, right? So the total E is done. Total E is done. Now we look at total IR. Total IR need to consider both external resistance and also the internal resistance. So we have 2 external resistance and 2 internal resistance. That means we will have 4 IR here. We have 4 IR here. We need to solve each 4 of them. Understand? Okay, now look at this R1 first. This external resistor R1. Okay, direction of resistor 1 depends on current. That's why we need to label the current near the resistor. Then only we can use the direction of current to compare with the loop. Understand? Okay, R1 depends on this current direction. The current is downward. Current is downward. And then the loop direction over here is downward also. You follow the direction of the loop. Okay? So when like you see here, when the current and the loop in the same direction, it is positive IR. Positive IR. Understand? So this current that passing through R1, yeah. For resistor, look at current. For the resistor, look at current. For EMF, look at negative to positive. Look at the terminal. For battery, for EMF, yeah, for EMF, look at the terminal. Look at the terminal from negative to positive. For resistor, look at the direction of current passing through. Battery, EMF, look at the terminal. Resistor, look at current passing through. So the current passing through R1 is downward. So the loop direction also downward. Same direction. So when current and the loop same direction is positive IR. So this IR1 is positive. So we write it as positive IR1. Understand? Okay. So and then what about the rest? Like this resistor 2. Resistor 2 also look at the current passing through. The current passing through also same direction with the loop. Same direction, so is also positive IR2. So it's also positive IR2. Positive IR2. And then now external resistance done. Now internal resistance. Internal resistance like R1 also look at the current passing through. Internal resistance also look at current passing through. The current is in the same direction with the loop also. So this is also positive IR1. Positive IR1. And then for resistor 2, the current passing through is to the right. The loop direction also to the right. You see? Loop direction to the right. So it's also same direction. So it's also positive IR2. So we have done all the 4 IR for all 4 resistor. Understand? So you see a lot of positive value, isn't it? A lot of positive value, except only one, except the E2 negative. All the rest is positive. Why you get such a beautiful equation? Because in the beginning you are wise. You use the very what I can say wise or intelligent loop direction. You try to make the loop direction. Follow the majority of current and EMF direction. That's why you make the loop direction to align with the direction of the current, align with the direction of the EMF, so that you get many positive value. But if you put the loop direction, let's say you put the loop direction, loop direction clockwise, is it solvable? Is this equation correct later on? Let's say you put the loop direction clockwise, opposite direction with the current and majority of the EMF. So what will happen to this equation? Then it will become this equation will become negative, and then positive. This one become negative, or become negative. Understand? Or become negative. So is this equation wrong? Is this equation wrong? No, this equation is still correct. So you want to put your loop direction anti-clockwise or clockwise, actually never mind. But if you put the loop direction like this, then your equation become uglier. Become uglier because you need to deal a lot of negative value, and we actually don't like negative value because we always make mistake. When we're dealing with negative value, we always do mistake, isn't it? So try to choose a wise decision regarding the loop direction. So try to make it more positive value. So the loop direction we use anti-clockwise is better. It's wiser to use this loop direction anti-clockwise because it follows the direction of the current and the EMF. So your equation looks more beautiful, more positive value, then easier to solve. Understand? Okay, that's all for this this equation we have built already. Now we just substitute the value. Okay, E1 is 12 volt. Just substitute the value and we can solve already. And then E2 is 4 volt. And then okay, you look at this. All this current is the same current, the same current passing through all the resistors, isn't it? So actually we can make factor out the current, and then all these resistors together, right? Resistor 1, okay, put the value of resistor 1 is 3 ohm, and then resistor 2 is 7 ohm, okay, and then R1 internal resistance is 2 ohm. And then R2 is internal resistance is 4 ohm. Okay. You see, we can get the current. Actually, the question also want to find current, isn't it? Want to find current. So very simple. We can do it. Yeah. Let's solve it. So 12 minus 4 is 8. This 3 plus 7 plus 2 plus 4, 16 I. What is the current? So this current is what is the answer? 0.5 ampere. That's the current value that passing through the complex circuit. We just solve it using the Kirchhoff rule. That's the function of Kirchhoff rule. It can find the current or voltage or anything in the complex circuit. Okay, so we got the current value passing through this complex circuit, the only one current, which is the 0.5 ampere passing through this single loop. That's the answer, 0.5 ampere. That's correct. Okay, that's correct. Okay, that's all for these questions. Okay, see you in the next video. Bye.